Hi, I'm Richard. You and I may be wondering why I am making this video. First, let me say that I am not a physicist nor a scientist. However, I am a retired engineer and I have always been keenly interested in how things work, and especially how gravity and magnetism work. Like a lot of people, I've looked for explanations. I have asked Mr. Google, watched YouTube videos. With all of that, I have not found anything which actually satisfies my gut. There may be something out there, but I haven't seen it. So I've spent the last few years thinking about fields and how they actually move things. A couple of weeks ago, I finally started thinking about it in a little different way. I stopped thinking about mass and just concentrated on the gravity field. The fact is, gravity does not attract mass, it only attracts the mass's gravity field. I now feel that I can explain how gravity works. Please note, I am not challenging any other theory of gravity. I am only expressing an intuitive theory to make it understandable to myself and the average person. In the next few minutes, I will give you a quick idea of what I'm talking about, and I would like to hear from anybody who has some comments or criticisms or whatever. So here we go. Thanks. So let me describe what we already know and hopefully all can agree on. Let's talk about the Earth, for example. The Earth has a radius of about 4,000 miles. The gravity field of the Earth goes way, way out into space. In fact, there's enough gravity at 240,000 miles to keep the moon in orbit. So the reach of the Earth's gravity is at least 60 times the radius of the Earth. This number can vary quite a bit. So gravity goes way out there, and let me say, if we were able to cut the Earth into a billion pieces, and we took one of those little billion pieces, and if we could measure its gravity in a zero gravity environment, the gravity field would probably go out 60 times further than the radius of whatever that little bit of Earth we had. So all mass has gravity, and that gravity goes way beyond the borders of the actual mass. When in a zero gravity environment. Everything has mass. Everything on your desk has a gravity field. Okay, now I want to demonstrate something very important, an important attribute of a field. That attribute is equilibrium. Here is a rubber band sitting on the table. Right now, it's in equilibrium. There is no net force moving any part of it. Now, I stretch it out. Okay? Now it is no longer in equilibrium. There are now forces trying to pull the rubber band back into equilibrium. When I let go, the rubber band returns to equilibrium, same as it was before I stretched it out. Here are two beads of water on some wax paper. They're little bubbles. They're in equilibrium. If we were in zero gravity, the beads would be perfect spheres. Imagine that the round bubbles represent gravity fields. When I bring the blue and red bubbles close enough to touch, we see that one brings in the other. They pull together and become one bubble in equilibrium. This effect of going back into equilibrium is central to how a field works. In order to describe the gravity field, I'm going to define what I call Richard's graviton, not to be confused with any previously described graviton. The graviton is the smallest bit of a gravity field. The properties of Richard's graviton is that it itself has gravity and is a force vector quantity which will always point to the center of the gravitational field, which often is the center of the mass, but not always. Gravitons that are in the mass are locked to the mass. You can't separate these gravitons from the mass. However, the gravitons outside of the mass can interact with other gravity fields. Each layer of gravitons holds the next layer above it in place. If nothing is interfering with the gravity field, then the field will always return to equilibrium. If we were to be in the center of the Earth, where all the mass is all around us, we would actually be in a zero gravity because all the gravity forces would cancel out at the center of the Earth. And there'd be no gravity there. If we were to march from the center of the Earth towards the surface of the Earth, the gravity forces would gradually get larger. And at the surface of the Earth, gravity would be at its maximum. As we went further from the Earth, the gravity would fall off rather quickly and then would continue to fall asymptotically towards zero far out into space. Mass and its gravity field are locked together such that when the Earth moves, its gravitational field will move with it. And if you move the gravitational field, the mass will move with it, like a dog on a leash. So as the gravitational field moves, it pulls whatever it's attached to along with it. So this is an important concept of what I'm trying to demonstrate. Now I'm going to discuss what happens when two gravity fields come together. Let's suppose we have two equal round masses, dark blue and light blue, and both are out in space, and they are approaching each other. In the illustration, we see that if we bring these two gravity fields together, we have gravitons on dark blue pointing towards its center, and then gravitons on light blue pointing towards the other way. And when they mesh and they enter each other's gravitational field, they will tend to cancel each other out because they're force vectors and are pointing in opposite directions. So both fields are torn and both fields will try to go back into equilibrium. Both fields will pull in gravitons from the interfering field and try to restore equilibrium. More significant is the fact the center of gravity is shifting to a place between the two masses, and consequently all gravitons will point to this new center, driving the two fields together along with the attached masses. Now here is a bus in zero gravity space. The gravitons on its field are all pointing towards the bus's gravitational field center. As the bus enters the Earth's gravitational field, the bus's gravitons will now point to the center of the Earth's gravitational field. Now here is the bus sitting on the Earth. In fact, the bus mass is now added to the Earth's mass, and the bus's gravity field has been added to the Earth's gravity field. The gravitons attached to the bus's mass are pushing it to the ground. Just try to pick it up. Imagine a ball rolls down on the ground. It keeps changing position, but its gravity field always is pointing down. As you already know, your weight holds you down because all the gravitons associated with your mass are pointing to the center of the Earth's gravitational field. Now, G, or gravity, is expressed as an acceleration. This can be confusing because gravity is really a force. The value of G is only the acceleration a mass m would experience when pushed with a force F. That is, the G value is the ratio between the force and the mass. This ratio of F over m is the same for all objects, big and small, at the Earth's surface, as Newton has kindly told us. Okay, let me reiterate the most important features of gravity. 1. All mass has a gravitational field. 2. An undisturbed gravitational system will be in a state of tense equilibrium, and when disturbed by another gravitational field, will try to return to a state of tense equilibrium by bringing in gravitons from the interfering field, thereby pulling in the interfering field and its attached mass. 3. Gravitons, or gravity, is a force vector which always points to the strongest gravitational center in a gravitational system. So there you have it. I hope I've cleared up some of the mystery about gravity. Thanks for watching, and please, any comments, I'd be very interested to hear. Thank you very much.